SwayamPrabha. Digital India. Educated India.
Yeah, we have completed the shrinking core model. I think except Renita, others were not there. So, you have to take notes from her, and we also discussed the extreme conditions like which are rate controlling, how do you find out the mechanism, which one is rate controlling, all that we have discussed. So, based on that, now I would like to give you an assignment. So, I will give you the parameters, you have to plot this assignment. I mean it is graphical, but each graph at least you should able to write on that graph at least 10 to 15 sentences. It is not that simply go to Excel and then plot and then give it, okay. So, that anyone can do whoever knows the computer programming, but what your expertise comes there is that if you are able to predict why something is increasing, something is decreasing, something is not increasing, decreasing, all that physical phenomena, right. So, the assignment is you take for example that equation number dimensionless equation number. What is that number? 23 or 24 in terms of Biot number and Damkohler number. Yes, equation number 23. Okay. Take equation 23 and plot xb versus theta. Theta is the dimensionless time, xb of course is the conversion. Okay. So, the range for theta will be 0 to 5 in the steps of 0.2. Okay, that means 0.2, 0.4, 0.6, 0.8, 1, 1.2 like that, right. Okay. And xb is of course 0 to 1 anyway, that I do not have to tell. So, what we have to do is A 1 Biot number equal to infinity. There are two numbers, Biot number and Damkohler number. So, and Damkohler number equal to 100, you have to keep Biot number infinity and change Damkohler number 0.1 and 0.01. So, then come to Biot number equal to 100, Damkohler number is same 0.01. Then Biot number equal to 10, Damkohler number is varied as same ranges 10, 1, 0.1, 0.01. Then we have Biot Biot number equal to I am going 1, Damkohler number equal to 100, 10, 1, 0.01. Then we have the fifth one, Biot number equal to 0.1, Damkohler number is same again 100, 10, 1, 0.1, 0.01. I think from this you will get almost all the information. xb is varying with Biot number. In that equation, xb is a function of theta, Biot number and Damkohler number. That is all, no? Nothing else is there in that. all are in the form of dimensionless numbers. So, then you vary, and now you have to say that for the comparison when you are plotting these graphs, for example, if there is a change between this and this, why there is change, the physical phenomena, or if there is no change between this and this, why there is no change, what is actually happening. And you know very large Damkohler number means which one is controlling, what is the Damkohler number definition? Yeah, large number means mass transfer, diffusion control, diffusion through the ash layer controlling. Okay. So, when diffusion through ash layer controls, then what kind of phenomena, what kind of things are going on within the particle. So, all that information you have to write, you have to write at least one 2 or 3 A4 pages, and then attach these graphs and then submit. Okay, it is left to you. Okay, if you do not submit, then examination, if you are not doing well, please do not ask me, right. Yeah, for the people who want to definitely pass, I think it is very difficult. I mean, I do not consider at all if you are not doing all this. This is only for your help. I may give the same thing in the examination. Okay, at that time, this is a practice. And the physics, if you understand after plotting and after writing, then definitely you will understand. And do not think that you are heroes when you copy. Copying is not heroism. Actually, solving and writing is heroism. But most of the time we will keep quiet till last day, and then last night we will just ask someone else's assignment, copy and give as if you fooled me. Actually, you are not fooled me, you fooled yourself first without doing. So, that is why these assignments, even though there are marks, I think you cannot only measure everything in terms of marks, you do not learn anything if you do really that. Okay. So, after this what we have to do is one other type reaction, type D reaction. If you have notes, can you tell me what is type D reaction? We will derive an equation for type D reaction. So, yeah, so this will be A gas plus B solid going to gaseous products, right. Yeah, what is the example? Gaseous yeah, combustion, gasification, there are very nice reactions where you at the end you will not see any particle, everything will be disappearing. So, that is the one for that kind of reactions. Now, we have to develop a shrinking core model, right. What is the difference? What could be the difference? Ash layer diffusion will not be there, okay, because every time the particle outer layer is first converted, then slowly it moves, and there is no, because everything is becoming gas and coming out, there is no solid product. So, that is why, and how we derive that we will see, and before that let us imagine our particle how it is moving. This is particle at time t equal to 0, maybe a cold particle. So, then after some time t, then we will have, this is the size, then after some time t, this is the one, and finally disappears into nothing. Okay. Yeah. So, now this is t, some time t. Yeah, okay, good. So, what is the difference is at time t equal to 0, just when you have the reaction started T 0 plus, for example, that is the film, then this is the film, then you will have this is the film, gas film. Right. It must be easy for us now to derive this, because there is no one more resistance there, there is no ash forming. So, there is no diffusion, and if you are able to plot the profiles, this is R equal to 0, that is the, and this is at any time I will call it as R C, and here we will call this one as capital R. that is initially at time t equal to 0. Then only the core is the particle is shrinking overall, but I am trying to maintain the same notation. R c is the diameter of the core which is shrinking, but the overall particle itself is core for us, not like in the other case where inside the particle you have a core, unreacted core which is shrinking, but here the entire particle is shrinking. So, as usual, now if I draw the profile like that is all. This is CAS. When it touches the surface, then reaction is taking place and the particle is slowly disappearing, because everything is becoming gaseous product. So, you will have this kind of situation at after some time t. Good. So, what are the steps now? We have step 1 is mass transfer MT of, we will go to abbreviations now, gaseous product, MT of gaseous mass transfer of gaseous reactant. Step 2 is reaction on the surface, Is there step 3? No. Why no? Yeah. See, the gaseous products have to come through the film again, no? Right? Yeah, they have to. Yeah, but we do not take that one. Step 3 equal to MT of product gases. Through film. Oh. But it does not matter for us, because it is not reversible reaction. So, that is why. Okay. So, that is why only these 2 steps we have to take, and at steady state mass transfer of reactant A going through the film must be equal to rate of reaction on the surface. So, that we know, we already are masters of that. So, then at steady state rate of mass transfer through the film equal to rate of reaction on the surface. Correct? Yeah. So, we know the equations now. So, this will be minus dNA by dt. If I write in terms of equations, this is simply rate 4 pi r c square, okay, and that is the area, and mass transfer equation, this is kg CAG minus CAS equal to, if I assume first order reaction, then this will be 4, reaction is on the surface every time, 4 pi r c square. Okay. Yeah. So, 4 pi r c square Ks CAS. Okay. So, this is equation 1. So, now of course, we have to eliminate this. I think I will write that in a slightly different way, so that some of you can get what is going on. So, this is if I write like this, this will be minus dNA by dt divided by all this 4 pi r square pi r c square kg. This is equation 2. Okay. You have to remember that CAC also equal to CAS. So, I think let me write that at least once. Okay. Then you are comfortable, no problem. Yeah, it is on the core, but now for us core itself on the outer surface. Okay, good. So, let me write this one once. Yeah. So, now CAS equal to again minus dNA by dt divided by 4 pi RC square Ks, correct? Yeah. So, from these two equations, from equation 2 and 3, what we can do is minus dNA by dt equal to 4 pi RC square CAG divided by 1 by kg plus 1 by Ks. Yeah. So, this is equation 4. So, this is our rate equation, but of course, if I want to make this one as a intrinsic rate, so then I have to divide by some area or volume of the particle or weight of the particle, whatever. Okay. So, 4 pi r square, that means I have just added these two and then separated again dNA by dt, that is all, very simple. Okay. So, now there is a problem here, I cannot directly integrate, and of course, you have another thing here. Our normal procedure is this equation just gives me what is the concentration profile or how the rate of reaction is taking place with respect to gaseous A, it is dNA by dt, right, dNA by dt. But what we would like to have is also dNB by dt, how the particle is shrinking, how the particle finally disappears. So, that is what we have to relate. So, for that we already have that equation minus dNA by dt, from this stoichiometry this comes, from this stoichiometric equation, equal to minus 1 by b dNB by dt, which is nothing but minus 1 by b d of, once more I will write, rho b Vc, correct, no, dt, yeah, which is again nothing but minus 4 pi RC square by b drc by dt. Here also we have rho b. Yeah, correct, thank you, rho b, good. So, this is equation number 5. Now, if I take equation number 4 and 5, drc by dt can be written as from equations 4 and 5 minus drc by dt equal to, yeah, can someone quickly tell? Yeah, b CAG by rho b into 1 by kg plus 1 by Ks. So, this is the equation which I am supposed to integrate to get the relationship between conversion and time or shrinking core and then time. This is equation number 6. Yeah, here only straightforward integration I cannot do. Okay. Why? Because now the procedure is take if there is any RC terms, I have to take this side, and time I have to take this side and then simply integrate. Is there anything which is changing with RC in the other side? Yeah, why? Why it is changing with K is changing with RC?
Film thickness? The film, no.
Oh. Film thickness is changing?
KS thickness is one.
Huh?
Only the particle.
Yeah. So, film thickness changes means what is indirectly changing?
Resistance.
Yeah, what is changing? What is the quantity? Yeah, kg. Kg is changing with RC. Do you have any relationship between kg and RC? Yeah. We go again to Ranjan-Marshall correlation. Okay. So, then we will see for small particles, for large particles, what is the relationship between kg and RC, and that relationship we have to substitute here in kg, and finally, we have to integrate, because now this kg is varying with RC. That means, if you take small particle or large particle, you will have, and I do not know, some of you would have done already something in Leonspiehl using Leonspiegel's book in non-catalytic reactions. You have done Anurag? Yeah, these non-catalytic reactions. He gives some very nice conclusions there at the end of the kinetic chapter. He has divided that into, one is the development of kinetic equations, other one is design. Two chapters are there on non-catalytic reactions. So, at the end of the first kinetic model chapter, he comments that when you have film control, the power to the r to the power of t is directly t is proportional to r to the power of 1.5 to 2. It goes. Many people do not understand that. I think now this is one of the basis is how you can derive that. That I do not derive, but I will just mention and then give it to you, so that I can ask that in the examination. Okay. So, t time is proportional to r to the power of 1.5 to 2. That means, as the particle size is decreasing, the exponent falls. Okay. Yeah. So, that you can get from this derivation. Good. Okay. Now, what we have to write here is kg is a function of Rc in equation 6, and you cannot directly derive that, I mean integrate that unless you know that functionality, right. So, that functionality can be, this functionality can be obtained from Runge and Marshall correlation. What is that? Sherwood number equal to 2 plus 0.6, Reynolds to the power of half, and Schmidt to the power of 1 by 3. This is equation 7. The same equation I can also write for easy solving. This is dP kg divided by d, that is diffusivity, equal to 2 plus 0.6, Reynolds number, it is dP u rho by mu to the power of half, and Schmidt number is mu by rho d whole to the power of 1 by 3. So, this is equation number 8. Okay. Now, we have to solve this. Okay. Let us see first for small particles. For small particles, the other term, Reynolds number term is neglected. Small particles means Reynolds number may be very, very small. So, this entire term may be smaller when compared to the one extreme, very, very small particles, right. For small particles, Sherwood number equal to 2, which is nothing but again dP kg by d equal to 2. So, from this what you find out? Kg is proportional to 1 by dP, correct, no, or proportional to 1 by Rc, radius, that is 1. And for large particles, this is what is the number? 9. This is equation 9. I will take, yeah. For large particles, Sherwood number, okay, equal to dP kg by d 0.6 dP u rho by mu to the power of half, mu by rho d to the power of 1 by 3. Yeah, now can you tell what is kg proportional to? Yeah, this is 1 by dp to the power of half, correct? Yeah, also proportional to 1 by rc to the power of half. Yeah, good. So, if initially our radius equal to capital R, right, initially, then in both the cases initially kg is no. Okay, I want to convert this into based on initial particle. Yeah. So, for small particles, where do you write? I think I may write here. For small particles, I can write initially kg by kg naught equal to kg naught. I will tell you, kg naught is the mass transfer coefficient initially, right. So, you will have here what is this? Yeah, r by rc to the power of 1, right, initially. And similarly here, so this is of course also equation 9a, 9b I will write here. Yeah. So, here also I can write the same thing kg, I think below also I can write kg by kg naught equal to, for large particles. Yeah, can someone tell? Capital R by rc to the power of half. Okay. So, in general what I can write, this may be 9, okay, this I will say 10. So, in general what I can write is, what I can write? So, in general what I can write is kg by kg naught equal to, if I take the ratio, r by rc to the power of n. So, this is equation 11, this is equation 11, and we have the two cases. If n equal to 1, no, the other way, for small particles n equal to 1, correct. For large particles n equal to half. So, I try to integrate this equation using substituting this, and then you will have both the cases. By substituting for n equal to half, you will have large particles and vice versa. There is another important thing also which I have not mentioned to you. There are some books like Carberry books, Carberry is slightly high funda book. So, there he also takes u variation with dp or dp variation u, particularly that is correct when you have moving bed reactors and also fluidized bed reactors. It is reacting, becoming smaller. So, when it is becoming smaller, then the terminal velocity, yeah, I think is higher and higher, because the particle can be easily thrown out. So, that variation of u with respect to u, how the RC is changing, the relationship between u and RC, that also is taken care of. But here we are assuming that u is constant for us and only d is changing. The other things are properties, rho and mu, they will not change, right. Here also diffusivity and all that, they will not change, only u can be changing, and that probably I will give in the examination some other nice trick there, and then I will ask you to do that. Okay. Yeah, good, because everything if I tell, you may not appreciate that. Okay. So, now it is only integration that is left now. So, that means from equation 6 I will simply write, from equation 6 minus integral, I have 1 by kg plus 1 by ks drc equal to integral, I will take the other thing, that is okay, B CAG rho B integral dt, this is 0 to t, correspondingly 0 means capital R, at any time t means RC. That is what I have to integrate, but I cannot integrate this straightforward because this Kg is a function of RC. So, that is why now again minus R2 RC, here I will substitute for Kg equation 11. So, if I substitute that, it becomes 1 by Kg naught into RC by capital N, that is one term, plus 1 by Ks into drc equal to B CAG rho B into T. Okay. Yeah, we also have an equation. We also have an equation for RC in terms of XB or XB in terms of RC. Correct? No, you know that. So, what is that equation? Yeah, we have RC by capital R equal to 1 minus XB power 1 by 3. Yeah, this equation I will call it as 12. Yeah. So, now this is 13. So, substituting equation 13 in this and then integrating, directly you will get in terms of time and then conversions. Okay. So, when you do that, what you get is substituting equation 13 in 12. Okay. I will write here using equations 12 and 13, what you get is T equal to, this mathematics you have to do, R B B Kg naught CAG 1 minus XB to the power of n plus 1 by 3 by n plus 1 plus 1 minus XB Ks by Kg naught. So, this is the equation. This is equation number 14. That is the equation. I think we will stop here. You have to go now. Yeah, we will stop here and then try to discuss this in the tomorrow. Tomorrow we will try to discuss about this particular equation, and Kg naught, you know, Kg naught is based on R initially at time t equal to 0, right? Yeah. So, again of course, you can also simplify this saying that okay, when film alone controlling or reaction alone controlling, that we will discuss tomorrow.